Hi, this lesson is on counting and permutations. You can stop the tape at any time and sort of think about the problem, and feel free to do that. First, we have a very simple counting principle. Sometimes it's called the multiplication rule. And it says, if you have to do a number of things, one after the other, it'll tell you how many ways you can do them all together. Let's take two things. Suppose you have two choices. A ways to do the first, and B ways for the second. And the total number of ways you can do these two things is the product of the two, A times B. If you have three things, for three choices or three procedures, let's say A, B, C, the total number of ways is A times B times C, and so on for any number of ways. Let's take an example. Suppose you have one room with, let's say, 10 men, and another room with, let's say, 9 women. And you want to find out how many ways can you pick one man and one woman. Number of ways to pick a man and a woman. Would be 10 times 9, which is 90, because you have 10 choices for the first and 9 choices for the second, so the product of these two is 90. Suppose you have 2 dice. Well, now I can use the color chalk. Suppose you have a red die and a yellow die. And you'd like to know how many ways these 2 dice can fall. Well, you know the red could fall any of 6 ways, and the yellow any of 6 ways. So the total number of ways 2 dice can fall would be 36. If you wanted to list these 36, it could go like this. You could get red on the first, and then any number of the yellow on the second. That's already 6 ways. You could get, I meant 1 on the first, any of these 6. You could get a number 2 on the red die in any of these. You get a number 3 on the red die and any yellow. Number 4, 5, and 6, in which each of these for the red, you have 6 possibilities for the yellow. It's like a multiplication table. You have 6 and 6, 36 ways to do it all together. Okay? Okay, suppose that you were to make a 2-letter password. how many passwords could you make? Each a letter of the alphabet. Think about that for a second. Well, again, you have two procedures to make. You have to make a choice for the first and a choice for the second. Since there are 26 letters in the alphabet, you can make, for a 2-letter password, (26 times 26 choices). That's 676 choices. How about a 3-letter password? Again, you have 26 choices for the first, 26 for the second, 26 for the third procedure. So it would be 26 times 26. 26 cubed, which turns out to be 17,576. This would not be enough, for example, for license plates in New York, because you have more than 17,000 cars. That's why a license plate has, let's say, 3 letters and 3 digits appended to it. Here's another example. How many phone numbers with 7 digits exist? So think about that for a second. Well, you have 10 choices for your first number, because any digit from 0 to 9 could be the first number. So 0 to 9 is 10 digits. 10 choices for your first number, 10 for the second, etc., up to 10 for the last one, 10 to the 7th, different telephone numbers. That's 10 million phone numbers with 7 digits. Now, that's not enough even for New York State, for example, and that's why we have an area code to add more possibilities. In some countries or cities where you don't need that many numbers, there are only 6 digits, or sometimes just 5 for a telephone number. Let's take another example. Let me move back here. Suppose a menu at a restaurant has 4 choices for appetizer, and let's say 5 choices for entree, and let's say 5 for dessert. How many ways could you make a meal if you had to choose one of each? And the answer would be 4 times 5 times 5 would be 100 different meals. All right? And one more example of the counting principle before we go on to permutations. Suppose that a student took a multiple choice test, say just 10 questions. 10-question multiple choice test. 4 answers possible for each. How many different ways could a student answer this exam? Well, he has 4 choices for the first, 4 for the second, all the way up to the last. 4 to the 10th choices, which is over 1 million. 1,048,576 ways that exam could be answered. Okay. Now, the counting principle is an underlying principle for many other formulas and principles. The first one we'll take is permutation. Now, a permutation is just an arrangement. You have a set of objects, and you're interested how many ways can you arrange them. Could be for artistic reasons, could be for economic reasons. You'd like to know how many ways you can arrange a certain set of objects. Consider 3 distinct objects. Let's call them A, B, and C. A, B, and C could be letters. A, B, and C could be people. A, B, and C could be different colors in a flag. A, B, and C could be bulbs in a chandelier. How many ways can you arrange A, B, and C? Well, by the counting principle, I argue this way. I have to make a first choice. Where do I put my first item? And I have 3 ways to choose the first item. But once I've chosen that item, my second procedure, that is choosing the second item, only has 2 choices. And the third procedure is now forced. I only have 1 choice for that. And by the counting principle, we multiply the number of choices in each. So 3 times 2 times 1 equals 6. And this says that the number of ways you can permute 3 objects is 6. And this is not hard to write down. Let's write down the 6 permutations. We can do it in alphabetical order. A, B, C, A, C, B. Then B starts off. And these would be my 6 permutations, or 6 arrangements of 3 distinct objects. If the objects are not distinct, if there were, let's say, A, and C, then I would not recognize a lot of these as different permutations. They would all look alike. In that case, we are going to have a different formula. Let's hold off for that for a minute. We're just considering now whether the objects are all distinct and recognizably distinct. If I had 4 objects to permute, my first choice 4 ways, my second choice 3 ways, next choice 2, and next choice 1, 24. And this would go on for any number of distinct objects. If I were permuting all of them, I would start with whatever all of them was, multiply that by 1 less than that, then by 1 less than that, all the way till I get down to 1. For example, 5 distinct objects allow 120 permutations. In general, you can see from this, n objects, and I stress here that they are distinct. That is, each object could be told from another object. allow n times n minus 1, because now I have one less choice for the next procedure, times n minus 2. And I continue that till I'm forced with the last object, which is 1. Rather than write this all the time, mathematicians have a name for this. This is called n factorial. And it's written like this, n with an exclamation point. And n factorial is defined as this product we just wrote down before, starting with n, multiply by n minus 1, by n minus 2, and continue till you multiply by 3, by 2, and by 1. So from the examples we had before, we've seen that 3 factorial is 6, 4 factorial is 24, 5 factorial is 120. And these numbers get large very quickly. For example, if you had to line up the 9 players in the baseball team, and a lineup is a kind of an arrangement, it's a kind of a permutation. If you had to line them up, the total number of ways you can make the lineup is 9 times 8 times 7, etc., 9 factorial. And that's quite a large number. Let me give you the exact value. 362,880. If you had to arrange 10 people, for example, for a picture, line them up, there are all kinds of different ways you could line them up. There would be 10 factorial, which just would be 10 times that, because I already have 9 factorial. This just reads 10 times 9 times 8 times 7 all the way down. And it would just be 10 times that. Over 3.5 million ways just to line up 10 people. So you can see these numbers get to be astronomical quite quickly. Okay? So, try this. How many ways to arrange 4 books on a shelf? Assume they're distinct. Think about that for a second. And you should have gotten 24. Another example, let's say you're playing Scrabble and you have 7 distinct letters on your tile board, and I stress that they're distinct. How many ways could you arrange them? The answer would be 7 factorial over 5,000 ways, 5,040 ways to arrange 7 distinct letters. Now, often we're interested not just in permuting n objects, but sometimes picking some out of the n to permute. For example, I may have a class of 30 people, and I'd like to pick a president and vice president. In that case, I would be picking 2 from 30. Or a baseball team. A baseball team really has 25 players, and the lineup is not made 9 out of 9, the lineup is really made 9 out of 25. In general, I could have n objects, and again, I'm assuming here they're distinct. And I want to permute R of these. For example, suppose I have 3 objects. But I only want to permute 2. I'll start with the same 3 objects I had before. Let's say A, B, C. And I want to know how many ways could I pick 2 of these to arrange them. Well, by the counting principle, my first choice, again, is 3, and my second choice is 2. And I would stop there. So there would be 6 ways of permuting them. 3 for picking the first item, and 2 for picking the next. In the next position equals 6. And here are the 6, if you want to list them. AB, AC. BA, BC. CA, CB. Notice that AB and BA each get counted, because in a permutation, it is exactly the order that interests me, how many ways something can be ordered. In some other problems, we'll see later with combinations, I would not count these differently because they're the same objects. But in the permutation, I'm particularly interested, how many ways can I arrange objects? So in a permutation, 2 out of 3 items, I have 6 choices. Suppose I had 3 out of 5 to permute. So I have to do 3 procedures now. Pick the first item 5 ways, pick the next item 4 ways, and the next item 3 ways. 1 choice, 2, 3. Equals 60. Suppose I want to permute 4 out of 7. 7 ways for the first, 6 for the next, 5 for the next. Here are my 4 choices. And that would be 840, permuting 4 out of 7. Let's go to the general case. I have n items altogether, n items. I want to permute not all n. If I did want to permute all n, then I would know it would be n factorial. But I just want to permute r out of them. Permute r from n. I start with n. Next choice is n minus 1. And I keep going. My last choice will turn out to be n minus r plus 1. For example, when it was 4 out of 7, I start with 7. 6, the last choice would be 7 minus 4, which is 3, plus 1 is 4. 3 out of 5, the last choice is 5 minus 3, which is 2, plus 1. Now this is given a name, PNR. And it's the number of permutations of R from N. Number of permutations, the number of ways you can arrange R items from N items. Again, we note that all these items are distinct, so every permutation can be recognized. Some notations are NPR for the number of permutations. Some are PNR. Some even switch the indices. But whatever it is, it's the number of permutations of R objects out of N. So let's take a few numerical examples. What would P64 be? Try that. It would be 6 times 5. Where would you stop? Take 6 minus 4 is 2 plus 1 is 3. That's one way to know how to stop. Another way is, since I'm picking 4 items, I know I have 4 choices. I have to put 4 numbers there. So this is 20 times 18, 360. Different ways to permute 4 out of 6. Let's say you have a flag. Choose 3 out of 10 colors. Let's say it's a flag that looks like this. First stripe, second stripe, third stripe, where the order of the stripes is important. So this flag could be made in, it's the number of ways I can permute 3 out of 10. $720 ways to make this flag. Okay? Now let's take that formula and rewrite it a little bit. This formula here, I'd like to work with it and get an alternate formulation for that. We'll start over here again. First, I'll take a particular case of that formula. Let's say P5, 2. That's 5 times 4. Because I have 2 items. I start with 5 and I have 2 items. Or the last term is 5 minus 2, which is 3, plus 1 is 4. That's the last term. Now you know that I can multiply something by 1 without changing its value. I'm going to multiply this 5 times 4 by the number 1. But the number 1 I'm going to write this way. That's the number 1 because, you know, assuming there's no 0 on the bottom, if you have the same on top as on the bottom of a fraction, it's the number 1. So this doesn't change the 5 times 4, it just multiplies it by 1. But now the top reads 5 factorial, and the bottom reads 3 factorial. So, extending that now to the general case, P and R, which is n minus 1 up to n minus r plus 1, and I multiply that by the number 1. Now how do I multiply by 1? What would be the next term going down from this? Well, the next term is always 1 less than this term. So the next term would just get rid of this 1. And the next would be all the way down. And I'm going to divide this by the same thing I multiplied so that I don't change the value. But now the top reads, since it goes from n, each succeeding term 1 number lower, all the way down to 1, this is n factorial on top. And on the bottom, I start with n minus r, and each term is 1 less than the preceding term. So the bottom is n minus r factorial. So we have an alternate formula for PNR. N factorial divided by n minus r factorial. So far we have 3 permutation formulas, total of 3 permutation formulas. We have if you permute all n distinct objects, and maybe I'll erase that now, I don't think I need it. N factorial ways. Permute r out of n PNR and an alternate permute r out of n and these two are really the same, it's just a different formulation of it. And we'll stop this lesson here.